avoiding slippage, techniques for creating a risk-adjusted schedule. For those of you who are attending for the first time, my name is Michael Trumper. I'm one of the principals here at Intabor Institute and been working in this area of project and risk management and software development for just about 20 years, and I am the regular presenter of these webinars. Before we start, we have a little bit of housekeeping, we call it, to go over, just to show you how you can use the GoToWebinar interface and how you can interact with the webinar. So hopefully you're seeing a pane at the top right-hand corner. You can choose your audio that you can interact with. I always recommend the mic and speakers if you have the computer. That tends to be a bit higher quality. And there should be a questions pane that you can see there. Now, during the webinar, you can ask questions. However, we're just going to put them in a queue, and we'll have a Q&A session at the end if any questions are presented. If you have any issues with the quality or technical issues that we might be able to resolve, let me know, enter it in, and we'll try and address that as the webinar goes on. Otherwise, we'll just wait till the end. So, as we start, generally, just to let you know that the webinars are relatively informal presentations on popular topics or features that our users have asked us about. Today, we're going to be looking at how we can reduce slippage by assessing and managing sources of risk in our project plans. I have a few more slides than usual, but I will get to show an example about how that might be, how you can adopt that in the actual software if you're a user or if you're going to be evaluating. And because there's a bit of long slides, if you can bear with me, I do promise to get to sort of a more live demonstration. So when we're looking at what we call project slippage, but we want to understand what the sources of risk are in our projects. And we look at the two main ones are what we call discrete risks or epistemic. They're risk events, and they can be characterized by a probability and it impacts, and the impacts can be across multiple what we call risk categories. Could be cost, schedule, quality, safety, going on. Key thing about them is that they're reducible. We can manage them. So we can take a look at them, and we can have the PMI is we can avoid, we can transfer, we can accept, or we can mitigate. The first two is that we're going to completely remove them from the project plan by avoiding or transferring. If we're going to accept, then it's probably low enough that we're okay with it. And the mitigation is the one that we can reduce it. So that means we're going to buy down that risk with various risk burn down activities or mitigation plans. The other major source is uncertainties, and it's also called aleatory risk, and it is the natural variance caused by randomness in all processes. The thing about them is they're irreducible, and that means obviously they can't be reduced. It means there's nothing really that we can do about them, but we want to make sure we can account for them. Now, between the two, really depending on the nature of the project, there are about 50-50. There are various schools of thought, or there has been research that showed one was much larger than the other. But what we're seeing really, right, more recently is that the risk events and the aleatory or the uncertainty, basically, you can account that they will be that they both will have about the same amount of effect. So you can you have a chance to reduce about half of this, or almost half of it. But if you don't account for that aleatory risk, that uncertainties, they will also could have a very big impact. And as we'll see, there's some other impacts that they, what I would call unveil or risk that develops out of the schedule logic that comes because of there is that aleatory risk. I would call it an emerging risk. And this is the emerging risk. It was because of parallel activities and merge bias. You might have heard that. And we'll show that. The portfolio effect, which happens on schedules and large schedules. And there's some others, what you might call schedule quality and estimate quality. There are minor things that are less impactful, but we need to account for them, or we need to deal with them, especially if we're going to be running the Monte Carlo simulations on your schedules. It's called there's a process. This is a standard slide that we have, but what it is, it talks about we have we have 5 steps in it, but 3 and 5 is where we're going to analyze and manage the risk events to come to a point where we can minimize the impact of those as much as possible. And step 5 would, once we sort of develop this and we get to a more detailed schedule, we want to run the analysis against some more detailed schedules that includes the uncertainties that we've identified in this project schedule. So the first thing that we're going to do, that we talked about, we're going to assess risk. So I'm not going to go through the whole risk workflow today, but what we want to do is we want to assess the impacts of risk on the projects. Part of this is we do this by assigning risks to the project. There might be other definitions used for that, but we call it risk assignment. And that means we identify risks with probabilities and impacts, and we assign them either to the project or whole or particular activities, run an assessment on that. And that gives us an idea of the possible impacts, and also gives us some insight about how we might be able to manage them. So we're going to put in a management plan about how to deal with the risks. The way that we can assess the risks, common ways are, these are 2, which we might have a risk matrix, which gives us an idea of what sort of management plans we have. Typically, depending on the color on the matrix, that will say what the strategy will be. For example, we have clients who will say anything that lands on the red means that they have to be either transferred or avoided. So they're not even going to attempt to mitigate those. They just want to, anything's on the yellow, they're going to try and mitigate them, and the green, or they'll accept them. The other way that if you're using quantitative risk, the risk score, in our risk register, we have a risk score that can be at a project, can be at a high level for all risks, or in all categories, or for cost or schedule. And this gives us this risk score really corresponds to the percentage impact of the overall variance for the risks in the project. But this, again, what it's doing here, like the matrix, it's prioritizing how you should look at your risks and the order in which you want to manage those risks. The ones obviously at the highest, you will manage first. You can also take a look, if you're doing a Monte Carlo simulation, there's different techniques to be able to pull out the cost of each risk, and that gives you an idea about the another quantitative measure about what the impact of those risks are and how much effort you should be putting into managing those risks. Again, these risks, the thing about risk events is they don't cause a sort of a gradual slippage. Generally, if they occur, they cause a sudden, abrupt change in the state of your project. You will see suddenly a big delay. And what we're going to be looking at in the next one is we'll be looking at uncertainties, and they are sort of a natural variance that occurs that don't cause these big shifts, but do cause a gradual deterioration of the project. So the second step is we want to assess the uncertainties or the aleatory risk. They are modeled, as we see here, they're basically used to model variances that are not due to risk events. They're modeled using statistical distributions with 3-point estimates. On the right, we can see a statistical distribution, and we can see that there's a frequency that goes on the y-axis and the duration, at least this is for a schedule, on the x-axis. The point on that is the most likely, and the optimistic is obviously on the left, and the pessimistic on the right. And really what we're showing is a sort of a continuous distribution of all the possible durations that could occur across from just about, this would be 3 days to 8 days. A little over, sorry, 9 days. 3 days to 9 days with a most likely of 5. So this is actually a fairly wide distribution. But there's all these possible, and we know that in this, at the peak, these are the values that are most likely to occur. And when we run simulations with the Monte Carlo, it takes into account this probability distribution. So it will turn values closer to the most likely rather than the ones at the boundary. So if we run 1,000 simulations, we'll probably only retrieve something right at the sort of boundary values, maybe once in 100 times, 1 in 100, 1% or 2%, based on how that distribution is created. So one of the things about, especially in schedules when we're looking at this, and the reason I'm going to bring this up is because it does have some, what I would call some of the emerging risks that comes just from larger schedules. Schedules and in schedules, distributions tend to be right skewed. So we have this we can have this long tail to the right. And the reasons for that is that we can improve a little off there. So we can, on an activity, if it's the most likely is, let's say, 4 days, we might be able to, if everything goes well and we're able to compress the activities, it might take, in this case, 2.5 days if everything actually goes. But there is no possibility that we can reduce it down to 0. It cannot. We can get it down to certain, but it will not. Our ability to reduce it is limited. However, on the right side, it's quite possible that this could go on forever, or more likely it won't go on forever. It'll be canceled because we couldn't finish it. That might be in a an R&D where you're trying to develop new technologies or new equipment. But as I said here, the room for improvements are minimal, but the ability or the chance that it could increase, the duration can increase, or if not limitless, there is quite a bit of room on the other side. So we do get these right skewed distributions with a long tail to the right. So when we are adding this to the schedule, it tends to look like this right here. So we've added, here's our project plan, and we've added these 3-point estimates. Now there's various ways you can do that. You can manually, or there's some tools just add them in, calculate them based on coefficients. But you can see on here we have various ones, and we have a distribution. We sort of say you can use triangular as the good enough one unless you have information to support another type of distribution. The thing about a triangular distribution is they tend to put a bit more weight on the boundary values. So you get a bit, rather than long skinny tails, you get a bit thicker at the ends, around the ends. So there is some discussion about which ones you should use, but from our own analysis, and we do have some stuff up on our site and on our YouTube channels, we have some analysis that we've shown that the reality is, especially between in one standard deviation, there's not a lot of difference that you look at using the different statistical distributions. So in this case, we call it the triangular is good enough, unless you can prove otherwise. So as part of the understanding and getting the slippage, so we are going to minimize the risk events. So we end up having some sort of residual risk. We can eliminate some of it either by transferring or avoiding, but some of the risks that we mitigate, the thing about them is that they are reducible, but we can't, when we mitigate them, we're not going to be able to reduce them down to zero. So there is some residual risk, and the risks that we put on the watch list, they represent some risk, and we're going to combine that with the uncertainties and run Monte Carlo simulation. And the point of that is that what we're going to do is develop some risk-appropriate or risk-informed schedule margin and cost contingency. And we call that a risk-adjusted project plan, but it's also realistic because it takes into account the level of risk. So you get a one that is, I call it the Goldilocks, is not too little and not too much margin or contingency, and it should get it just right if you have it at the right level, if you use the right sort of what we call certainty levels. The other side of that is when we want to, I just want to bring this in, is that you want to be able to, when you're running a Monte Carlo, you have to have a high quality schedule. There's a few major things. If you went in and one of the standard methodologies or processes, it's called the DCMA, which is the Defense Contracting Management Agency, but they have a 14-point basic assessment that they use. But what we want to make sure is that the schedule logic is strong enough that you can update the project automatically. So that if you make change on one activity in terms of duration or some other parameter, that it will push, and it will update all the activities. So if it becomes longer, all of its successor activities will get pushed out because of that. So that means we don't want to have dangling tasks. So tasks that don't have a successor or predecessor unless they're the first and last. And we want to check for circular logic. Those are really the basic ones. There are a lot of schedule checkers available. I'll give you a sneak peek at our upcoming version, where we have some additional new schedule checker that we're going to include with the new professional version, and it will provide a 14-point DCMA analysis. The other part is, and this can't be helped, but it's the estimate qualities is you get garbage in, garbage out. You want to make sure that you're getting as high quality as possible. There's a lot of information about how to improve your estimate, the quality of your estimates. I just put in a few bullet points here, but I thought I would include that because people do bring that all up all the time. Yes, we have all of this, and it could be the logic and all of these. You have all of these things in there, but if the estimates are off, yes, that's goes without saying. So I thought that I would include that. That is a source of risk. So why do you have to use Monte Carlo as opposed to, let's say, critical path? And I've just brought up two PERT. Critical path, it's deterministic, and it measures the longest possible path that the project plan, the schedule could take. The problem with it, it doesn't account for uncertainties, and we'll take a look at some of the things that it doesn't account for. And PERT is a program evaluation review technique. It was developed in the 1950s as part of the rocket and missile programs that the U.S. government was undertaking, and it was a way of assessing the quality and the duration, if we want to do a schedule analysis of the programs that they had. It uses a weighted average, and a lot of times it is good enough on smaller schedules. But what happened over time is they found, and there's a little formula there. What happened is over time, they found out that it was just the results that were given were still too optimistic, and the reason for that is, I'll bring this up, is two sort of emergent risks that I've called that come out of because of the schedule logic and the nature of schedules. So one of the things that happens is it's called merge bias. I call it parallel activities in near critical tasks. Is that if you have activities where you have activities that are occurring in parallel and they all have to merge into a single activity. This one is very simple. We're just showing five activities that have a start. If they have no uncertainties on them, activity one in this view would always be on the critical path. However, if we have five activities and we have uncertainties associated with them, what happens if we look up here, we can see that this has a 5 days. What's happening in here because of the uncertainties, the mean duration, the average, is now being shifted out to 6 days. So it's gained an additional day on here because of the near critical task. And the reason for that is that if we look at these little distributions here, at any time one of these activities which has whose base duration is 4 days can actually jump out and become critical. And if we have large activities, there's going to be multiple, many large project schedule, detailed project schedule. You're going to find that there's going to be lots of merge points that occur during the project schedule, and this effect starts to accumulate. And in what we call it in Monte Carlo, we have something we call crucialities, like how often how often is a activity likely to hit beyond the critical path. Rather than in critical path where there's only a single one, we say there could be, when we run a Monte Carlo simulation, we have the chance of having multiple critical paths occurring depending on on each iteration, what sort of values that are used during running that. So that's one sort of emergent risk that occurs because of the nature or the logic of a project schedule. The other one is what we call the the combination of the right skewed distributions and portfolio effect. So in right skewed distributions, one of the things that happens is that the mean is higher than the P50 value. Now, and the P50 value is higher than the most likely. And what happens is when we have large large precedent network where we have predecessors, successors with right skewed distributions, and they're relatively uncorrelated. What happens is that I'll just go on to the next example here. This would be an example file, 5 days. We have 10 activities each 5 days. So deterministically, it would be 50 days. If we run a Monte Carlo simulation on that, and we have these 5 days and they're right skewed, what ends up happening is the P50 now, or the mean, is now 53 days. What happens is that the P50 actually moves to the right, and the S-curve actually tightens around the mean. So if we had a relatively flat one for each distribution, what the overall impact the cumulative results of all of these distributions together, we get a much tighter, steeper S-curve. But not only that, is it shifts, it becomes steeper, but it shifts to the right. And what that does is it means that we have obviously the P50, but the chance that we're going to meet that deterministic becomes increasingly small. And in this particular one, we only have a 9% chance now that we're going to meet that duration of P50. The point of being this is that the combination of these two emergent risks, merge bias and the portfolio effect on the schedules, is that it can account up to a 20% possible slippage if they're not accounted for properly. And the way that we account for them is adding additional, making sure that we have enough schedule margin, a buffer, and contingency in the project schedule to account for that, so it doesn't doesn't catch us by surprise, so to speak. And the only way that we can account for these, the only way that we can accurately account for the merge bias and portfolio effect so far is by running a Monte Carlo simulation analysis. So we're just going to say once we've run this analysis and we've included the residual risk and we've included the uncertainties, we can then start to take a look at how we're going to develop the enough contingency in our project plan to protect our deliverables. So typically our contingency or our schedule margin, based on what we're looking at, if we're looking at schedule or cost, is going to be the difference between our baseline and a level of confidence that we have set. The level of confidence typically commonly is P80. That means we're setting our contingency or buffers at a level that is 8 out of 10 times we'll be able to make that. That's considered fairly conservative. There is a little bit of risks there, that we could overrun that, but it has enough confidence level rather than if you're running at the most likely or you're running at a P50 or deterministic, you're still, what that means is you're going to be running a P50 really means you have a 50-50 chance of meeting that. Not bad way to set your internal project's plan, but the buffer should make up the difference between that P50 and that P80 or whatever confidence level that you set for an organization. And we calculate that using the Monte Carlo simulation. Really, that's the only way that we can account for the uncertainties and those emerging risks that occur with emergent risks that occur with merge bias and the portfolio effect. So when we do that, I'm just showing here is basically if you look at the smaller triangle, that's our original project plan, and we're going to add contingency and margin at a level. In this case, we're showing it as P80, and that doesn't mean if one of the questions that I do get, well, P50, so that is, and we're putting it, does that mean we're adding 30% to our budget or 30% to our schedule? And no, that's not what actually percentage means. It's a certainty level, and it doesn't equate it doesn't equate at all to percentage of the budget or the schedule. And oftentimes, depending on the nature of the project, if it's a very relatively lower risk one, that could mean that you're just adding, it could be like 5%. However, if it's a very high risk, lots of variance in it, lots of uncertainty, lots of risk, that P80 could be considerably more, but it doesn't actually equate to a percentage as opposed to a traditional way of just adding a percentage for cost and a percentage for schedule. We're actually going to use what we're going to use a standardized certainty level. And one of the reasons what's good is that you can apply this certainty as a standard across all of your project, and it means that when you assess your projects and you're doing an analysis at a portfolio level, you can see the sort of risk and cost and base it on a standardized level, what we call certainty or confidence levels, about in terms of how many resources or finances you're going to have to put aside to cover that risk and uncertainty that you have in those projects. So I'm just going to summary slide here, but we just want to be able to reduce the slippage and impact of slippage by managing, controlling risks, which are reducible, and accounting for uncertainties and integrating sufficient schedule margin and management reserve based on the analysis. And the only way, again, I'm just going to say, the only way that we know so far right now is to be able to do it running a Monte Carlo simulation. Now, how does this look in a project plan? So in our software, we can add risk to the schedule. You can see here that we've assigned risks to various ones. Risk assignment can occur in many different places. We can assign risks using this interface here. We can assign risks by selecting activities, selecting an activity and dragging them across. We can assign risks that one doesn't have a risk. Let's try that one. I seem to be missing. This one always has risks. Okay. And we can assign risks here. You can see how these have been assigned to a particular activity. And it's one of, if we assign them use it through the risk register, they will appear here. If I assign them here, they will appear in the risk register. So it's just multiple points of entry depending on what you're comfortable with. And we assign them to the risk and they would appear. I'm just going to close that off. They would appear in the project schedule. Once we run a simulation, we can see them here on here. Risks would appear going down. Opportunities, if we had them, would appear going up. And the color, we have color coding based on the criticality. The other thing that we want to be able to do is we want to be able to assign uncertainties. And here we have our base schedule. This is our deterministic one. And we can assign low estimates and high estimates with the statistical distribution. We have the current method to do that is to select activities and set low high duration, and we can calculate these. So we can enter them manually, or we can go select groups of activities and enter have them calculated based on coefficients, which is a very standard way of doing it, and then applying a distribution type. Or we can do it using fixed values, so we can do it as select activities and assign based on the number of days or whatever duration values that we want to. On groups of activities, obviously correlate because it will increase it relatively. This one we don't see too often. It's just as easy, but applying fixed duration to groups. If they have the same durations, it makes sense. If they don't have the same duration, this one is probably the way to go. One of the things is I've got a testing version right now. We're adding what we call uncertainty bands, which can be developed, which can be modified depending on, and we can assign them based on. And then it would assign this, and it actually provides a color coding to that if we wanted to do that. I'll just show you another one. This is something that's coming out with version 7.1, and we can see that now that goes to yellow based on the level of risk for those activities. So it's a good, what I would consider a reasonable way to visualize the amount of risk that we have in these activities. So out of this, we end up having our uncertainties, and we have our risks that we're going to assess, and these are, without going in, these are post-mitigated risks. And we can also, the other thing is we want to do a schedule check. We have in version 7, we have a simpler schedule. We're going to be introducing this larger, more complex. This is a full DCMA 14-point analysis. However, again, this is not a requirement, but you do have to have a schedule that has the logic is that it can be updated and doesn't have circular logic. Those are really the two main things. But if you want to make sure that you have enough, and also I should say constraints. We want to have soft constraints as much as possible, because fixed constraints will artificially fix activity durations. So once we run that analysis, we can start to look in analysis views, and we can either look at it at the project level. Let me just drag this down a bit. So if we're looking at schedule, and it looks like I didn't add the P80 to that. We'll add P80 to that. And here's our P80, and I can just drag this over. This is a quick way that we can start to take a look at, and we can see here is our deterministic, and here is our P80. The difference between this at the project level is about 11 days, maybe a little bit more than that, 11.5 days. But that gives us what our schedule margin should be based on the certainty of P80. So this is based on our model, our 8 out of 10 times we'd be confident we can finish in this time. So we can set that based on the difference between our deterministic, which is our plan, and the results at the P80 level. Again, we could do that also for the cost. Typically, when we're setting this, whereas cost contingency and margin, we're more likely, or the best practice is when we're doing it is to set it at the deliverable level, so that once we've finished an activity and completed it and moving on to the next one, we can retire that. So if you want to set and see what sort of contingency and margin you should be setting here, one way is to look at it is to, you can see the difference between the, between the high duration is P80 here. You can see the difference between the high and the base duration, 23.5. So this one would end up having about 5 days margin for this activity, and we would put a margin activities directly into the schedule, and we can do the same thing with cost, or we can pull that out and we can look at a probability again, and we can do the same sort of analysis here for each one of these deliverables about how to develop that. And we can also do that at the cost level for cost to figure out what sort of contingency we should have for these deliverable as well. And the difference would then again be the difference between here and here. We can see that visually here, or we can pull that out from our deterministic versus our P80 value. And that's about about $80,000 there would be the contingency for that. So with that, I'd like to finish up now. If you have any additional questions, please, I can review them right now. If not, if you're interested, we have these are 3 books. This is our last book that's just was published in 2017 through the World Science publisher. Project Decisions was our first book that we put out in 2007. We're going to have a second, hopefully having a second edition coming out upcoming this year is the plan. We do have a lot of additional resources. If you want to take a look, one that's we have a presentation, and we'll probably have this webinar posted in the next 48 hours. And we can make the slide deck available if you're interested. White papers and articles. We have online tutorials, and we have what we call a non-commercial project decisions, which has a website which has many different links and resources for people who are interested in finding out on additional information on topics such as this and other project risk analysis and management topics. So it doesn't appear that we have any questions today. If you do have any questions, please feel free to contact me directly. Mike Trumper at intaver.com. There's our number up here in Calgary for our office. Be happy to discuss anything with you. Or if you'd like an online demonstration, please let me know. If not, thank you very much, and hope to see you at one of our upcoming webinars in July.